The lead-lead isochron method, which is the method currently used to estimate the age of the Earth, it's difficult. So I've created this little video to try to explain how it works and show you exactly what Claire Patterson did in his famous 1956 paper to estimate for the first time an age of the Earth that has withstood scrutiny and withstood testing for many, many years. That age, of course, is 4.55 billion years. So all of this is based on the decays of uranium to lead. Now, in fact, there are two different isotopes of uranium that are unstable that decay to two different isotopes of lead. Those are 238 uranium, which is the most abundant form of uranium, which decays to form lead 206. And then we also have, when this has a half-life of about 4.5 billion years, so it's quite slow, this process. The other radioactive form of uranium is uranium-235, which decays through a bunch of intermediaries and finally ends up at lead-207. And this has a half-life of about 700 million years. So it's a process that's somewhat faster than the decay of uranium-238 to lead-206. And the lead-lead isochron method takes advantage of these two processes going on simultaneously whenever there's some uranium in the rock. If there's uranium in the rock, there will be a certain portion of it that's uranium-238, which will decay to lead-206, and a certain portion of that uranium will be uranium-235, which will decay to 207. And if we keep track of all those different isotopes, we can actually determine the age of a sequence of rocks using this lead-lead isochron method, which I'm going to describe now. But let's first start out and just write the straightforward decay equation we could do for any of these decay schemes. That's just based on the standard equation of parents and daughters, right? And that equation would be, for the case of uranium-238, that the daughter isotope, 206 lead, is equal to the amount of 206 lead originally present in the rock plus the amount of the parent, 238 uranium, times the decay term, which is e to the lambda 1 t. I'll use lambda 1 as the decay constant for uranium-238 minus, and I'll use lambda 2 for the decay constant for the decay of uranium-235. So, and then for uranium-235, I could write the same thing, which I'll do real quick here. Okay, there's the equation for the decay of uranium-235, producing the daughter of lead-207, right? And these should look familiar. We've used these before when we described the decay of rubidium to strontium, for example. Now, in addition to the 206 lead and the 207 lead, which are leads produced by radioactive decay, there's another isotope of lead, lead-204, which is both stable and not produced by the decay of any other isotope. So the amount of lead-204 in a rock doesn't change. It's not added to by decay, and it itself doesn't decay. So what we can do then is we can take both of these equations, as you might expect, and we will divide them by the stable isotope 204 lead. And this generates the two equations in terms of isotopic ratios that we commonly use when we do radiometric age dating. So let's see what those are going to look like here. And we will do them. Let's do them in purple. Why not? Okay. So what they're going to look like. I'll write the first one out, and then I'll very quickly write the second. So we'll get 206 lead, the ratio of 206 lead to the stable 204 lead. And that is going to equal the initial ratio of 206 lead to 204 lead plus the ratio of the radiogenic 238 uranium to 204 lead times the decay term, e to the lambda 1 t minus 1. And I can do the same thing for the second equation by dividing by 204 lead. Okay, there it is. Now, if we look at this equation, once again, let's think about what kind of unknowns we have and what kind of knowns we have. Well, we did this before with rubidium strontium, right? So we can directly measure these isotopic ratios, these lead isotopic ratios here. We can directly measure that, and we can directly measure the isotopic ratios of uranium and lead shown in this term here. In addition, some things are known. We know the decay constants, lambda 1 and lambda 2. Those are constants that are known. So the unknowns here, I guess I'll put them in blue. The unknowns here are the time, the age of the rock, and these initial ratios, 206 to 204 lead and 207 to 204 lead. So we also don't know the 206. I'm going to write this as 206, 204 lead as a shorthand, that initial ratio. And we also don't know the 207, 204 lead initial ratio. So we have 3 unknowns and 2 equations, and so once again we can't solve this without some extra information. And so let me try to graph this up so I can show you actually how this works. This is going to make a lot more sense when we show you this in a graph than algebraically. But I think it's important to show the algebraic equations here first. Actually, before I do that, let's consider, if we're interested in the age of meteorites and the age of the rocks, let's physically consider what happened early in the history of the solar system. So early in the history of the solar system, we formed lots of little bodies called planetesimals. Well, here's some examples. Here's a couple of planetesimals. The larger planetesimals may have survived to become planets. But let's just show 3 little planetesimals here. And some of these planetesimals, they're sort of Earth-like bodies, right? And they underwent an origin similar to Earth, and they underwent a development similar to Earth. So in many cases, they developed a core due to melting and the sinking of the immiscible iron-rich liquid to the center of the planetesimal. So some of these developed cores. These are supposed to be in the middle, right? And maybe some of them didn't get hot enough to do that. So I'll leave this one over here without a core. And then these little planetesimals, these all formed nearly at the same time when the Earth was forming at the beginning of the solar system's history. And then they crashed into each other and broke up. And those little pieces of these planetesimals are meteorites. So meteorites represent meteors, or meteorites when they land on Earth, represent pieces of these planetesimals that had a history very similar to Earth and formed at the same time as Earth early in the solar system history. So let's imagine then what these pieces might look like. We could grab a piece here from the mantle of one of these bodies. We might even grab a piece, an iron meteorite, from the core, and this one over here might have a piece of the undifferentiated body, and here's another piece of a mantle of a planetesimal. Now, here's a key point. During the differentiation process, when the immiscible iron-rich liquid sank to the center of the planet and the silicic liquid rose to the outside, that process differentiated uranium from lead. So as that process happened, uranium tended to be concentrated in the mantle, and lead relatively less. It's concentrated in the mantle to a lesser degree. I'll put concentrated in the mantle to a lesser degree. And what I mean by that is the ratio of uranium to lead is higher in the mantle of these little planetesimal bodies, was greater than the ratio of uranium to lead in the core. So these meteorites that were derived from either the core or the mantle have different ratios of uranium to lead. That's going to be important in a little bit. So for example, this one here, let's call this, let's give it a color here. This meteorite here has a higher uranium lead ratio than this meteorite here, because this one here comes from the core and that one came from the mantle. But now, having said that about uranium and lead, remember all of these formed at the same time from the same nebular dust, and within that dust, the ratios of lead isotopes of 207 lead to 206 lead to 204 lead are going to be the same. These ratios are going to be the same for each of these meteorites, because those ratios don't change when the planet differentiated. These isotopes chemically behave exactly the same. So when the planetesimals formed from the solar nebula, they incorporated exactly the same ratio of lead 207 to lead 206 to lead 204. So the initial ratios of 207 to 204 and 206 to 204 were exactly the same in all of these meteorites, even though their uranium to lead ratios may differ. Now, so that's physically what's going on. Now, let's see again how these things are going to plot in our classic isochron diagram. This is what a lead-lead isochron diagram looks like. We are plotting the ratios, the lead ratios. So on the y-axis we plot the ratio of lead 207 to lead 204, and on the x-axis we plot the ratio of lead 206 to lead 204. It's important to remember where these leads come from. Lead 206 here comes from the decay of uranium 238. So uranium 238 is decaying to form lead 206. And remember, this has a relatively long half-life of about 4.5 billion years. Lead 207 comes from the decay of uranium 235, which is decaying to lead 207, and this has a slightly shorter half-life of 700 million years. So as rocks age, both of these ratios will increase due to the increased production of lead 206 and lead 207, right, from different uranium parents. Now, let's look at where those meteorites we talked about earlier would plot on this diagram. In fact, let's imagine three different meteorites here. I'll have the pictures of them right here. So this is meteorite number 1, and it has a very low uranium to lead ratio. And then meteorite 2 is a green one here, and this has an intermediate ratio of uranium to lead. And then meteorite 3 has a high ratio of uranium to lead, just depending on which part of a planetesimal it came from and the evolution of that planetesimal prior to the time when it broke up into pieces. Remember though, despite there's no uranium and lead on this diagram, right? This diagram just plots lead-lead isotopic ratios. And remember, we said before that all of these things, because they formed all at the same time, have exactly the same ratios of 207 to lead to 206 lead to 204 lead. These ratios are exactly the same in each of these meteorites. So that means on this diagram, they're going to plot in exactly the same spot with a lead-lead concentration that is the initial concentration when they formed. So let's show how that works. First of all, let's define these initial concentrations right there. This here is going to be 207. I'm just going to call this 207, 204. Understood that that means lead initial. And over here, I'll call that the 206, 204 initial concentration of lead. So all of these things are going to plot right at that point right there. So let's show this in a nested fashion. So there is the first meteorite like that. And then the green one with slightly more uranium is going to plot right on top of it. I'll try to draw that as a little like that. And then the blue one with even more uranium is going to plot out like this somewhere. Okay, so they're all nested. They're exactly in the same location. I've tried to show that they all appear there, but they're all plotting at exactly the same location. Now, so this is their composition. This is their isotopic composition when the rocks formed, when these meteorites formed. Now, what's going to happen to the isotopic composition as they age? Well, as they age, we're going to produce 207 lead from the decay of uranium-235. So this is going to go up. And we're going to produce 206 lead from the decay of uranium-238. So this is going to go up. So both of these ratios are going to go up because 204 lead doesn't change. So that means that all of these compositions are going to go on a trajectory that shows an increase in both ratios of 207 to 204 lead and 206 to 204 lead. Now, let's start with the blue one because that's kind of the easiest one to show. Initially, what happens to this composition is it follows a path that is rather steep like this. And the reason it's steep is because the half-life for uranium-235 forming 207 is shorter, and so this 207 lead forms more quickly than 206 lead, which is formed by the decay of uranium-238 with a much longer half-life. So initially, we have a steep slope, but then as we sort of exhaust the amount of 207, exhaust the amount of uranium-235, this curve begins to follow a path that goes sort of like this. So after some period of time, this composition, the blue meteorite, which had the most amount of uranium, therefore is going to produce the most amount of radiogenic lead, both 207 and 206, is going to follow a path given by this blue line like that and end up somewhere over here. Right over there. Now, what about the green meteorite? The green meteorite had a little less uranium in it, so it's not going to go as far away from its origin here in the same amount of time. Because it's got less uranium in it, it's going to produce less 207 lead and less 206 lead. It's going to follow a path which has a similarly curved shape, but it's going to sort of go like this. So there is the path taken by the green meteorite during the same period of time. And finally, our red meteorite here has the smallest amount of uranium, so it's going to move very little from its original position. In fact, if it didn't have any uranium, it wouldn't move at all, right? Because if it didn't have any uranium, then the concentration of lead-206 and lead-204 wouldn't change because there's no uranium to decay into those isotopes. But let's say it's got a little bit of uranium, so it's going to move a little distance here like this. Now, each of these lines represents the path in terms of the isotopic composition that meteorite has followed during this period of time. And if I've done this right, what you should see is that each of these three compositions lie along a line that goes right through the original composition. Let's hope I did this right. Very hard to draw this like that. Okay, this here this line here, once again, is called an isochron. And just like with the rubidium strontium system, the slope of this isochron corresponds to the age of these three meteorites. As these meteorites grow older, what's going to happen is that they'll continue along their path like this. I'll just make them a little bit older now. So this is a little bit older. They're continuing to evolve like this. Oops, that's supposed to be a continuation of that line. And this line's going to continue. This is the one that's hardest to show, right? Like this. And so the new, after a slightly longer period of time, the isochron will look like that. So this is isochron 2. We'll call that isochron 1. And isochron 2 is the isochron you get if the rocks were slightly older. So you can see that as the rocks age, the slope of the isochron diagram becomes flatter and flatter. So as the rocks age like this, in this direction, the slope gets less steep. So we can relate the steepness of the slope to the age of the rock. In addition, we also can see that all of these isochrons are going to pivot through this point down here, which represents the initial concentration of lead 206, 204, and lead 207, 204. Okay, so that's the way the isochron diagram works. Well, let's look and see what Patterson actually did. This is really clever. Well, Patterson actually plotted the composition of real meteorites. Here, once again, is our lead-lead isochron diagram. And the first really clever thing he did was he found a meteorite that was an iron meteorite. That is, it came from the core. And within that meteorite, he found some minerals, these minerals called troilite, which formed at the same time as the core. But this particular mineral had virtually no uranium in it at all. So the uranium-lead ratio in this troilite was essentially 0. And therefore, its lead-207 and lead-206 compositions never changed throughout its history. So so when he plotted this troilite up, this iron meteorite troilite, it sort of fell right over here, and its history is real simple on this diagram. It doesn't change. Because it didn't contain any uranium, it couldn't produce any more 207 lead or 206 lead, and so the ratios of 207 to 204 and 206 to 204 never changed. So this troilite identified for him the initial ratios of lead in all of the meteorites, because they should have had exactly the same initial ratios. So again, I'm using the shorthand of 206 to 204. Implicitly, that means lead. The initial concentrations, the initial ratios of leads can be found from this troilite. He then plotted up some stony meteorites, which had higher concentrations of uranium and therefore evolved away from that initial composition, right? And he found that they lay sort of over like this. So these are the stony meteorites, and this red one was the iron meteorite. And lo and behold, he then could fit a curve, an isochron curve, went right through these data and defined an age of 4.55 billion years. So using this method, he determined that the meteorites all formed at the same time with the same lead ratios 4.55 billion years ago. Now, that's meteorites, right? So the question then is, well, what about the Earth? To investigate whether the Earth looks like it had a similar history as these meteorites, he looked for some material from the Earth that would represent the bulk composition of the crust or mantle that formed at the same time when the crust or mantle did early in Earth history. And so what he took is a bunch of oceanic sediment. So the oceanic sediment was derived from erosion of all the continents all over the world, and so it's a good estimate of the bulk composition of the Earth. And when he plotted that oceanic sediment, lo and behold, the oceanic sediment fell right on the line. So the oceanic sediment from Earth, I'll put that in big letters here, falls right on the same line. And the conclusion, therefore, is that this bulk material from Earth Earth must have had a similar history to these other meteorites. In other words, it must have started down here with the same initial compositions of lead and then evolved along a path that in 4.5 billion years took it to there. And just like the other meteorites, it falls along the same, oops, it's supposed to go right through that line, the same isochron line. So in 4.55 billion years, the Earth evolved and fell right exactly on this line, which suggests, which implies that the Earth must have a similar history to the meteorites. It must have formed at exactly the same time with exactly the same lead-207 to lead-204, lead-206 to lead-204 ratios, and evolved just like the meteorites so that today it lies along the same isochron as the meteorites. This is the evidence then that the Earth is 4.5 billion years old, just like the meteorites.